So today we're going to talk about across, through, classification. And in this classification, we're going to be converting, for example, mechanical systems to electrical systems, or electrical systems to mechanical systems. And this actually requires the use of transferring of effort to flow. And here will be flow to effort. However, but this is not considered effort flow classification. This effort flow classification is actually the classical modeling, and it's not the same. So to begin, basically, we're gonna start with a very simple example. Call it example one, example whatever. So this diagram, we're gonna take something such as something in parallel. So in parallel, we will take something. Let me look for a question. If I have a boundary and I connect a damper and a spring in parallel, and then I put another spring in series, and this is a free end, and I'm going to call this D, I'm going to call this S1, and I'm going to call this S2. So what we know right now, and given this line of action, we're going to say that the question is given to us like this. We have a specific force being applied on the free end. So from here, what we know from our previous videos or previous class is that we know the spring exerts a force opposing the motion itself. So we call this S2 and FS2. And here we're going to say that we have a damper opposing the motion with FD, and another spring opposing and with FS1 and FS1. So now we have one line of action, a second line of action, and a third line of action. So at our line of action of number one, I should write it here. We say that, as I said before, like in the equation of we start with the equation of balance. You always start with the equation of balance. So in the equation of balance, always the sum of input is equal to the sum of output. So the sum of input, we will say that F0 is equal to Fs2. And our second line of action, we say, again, the sum of input is equal to the sum of output. So therefore we say Fs2 results in Fd plus Fs1. And in here again, our third line of action, we say the sum of input is equal to the sum of output, which would be equivalent to Fd plus Fs1 would equal to our F out, but in this case it's 0. So we're gonna transfer this from an effort to a flow. Effort to flow. Effort to flow. So I don't know the explanation why, but this was the concept that the people that came up with this is that usually if we were to, the effort equivalent in electrical systems for force would be voltage. But in here, we're going to take the flow variable instead of the effort variable. So we take I0 is equal to, and we have a spring, and the spring equivalent in electrical system is an inductor, because a mass would be a capacitor. So we call this FL2. And a simple way to remember that a spring is an inductor is that an inductor if you know an inductor looks like this, but within that inductance itself, you actually has a spring inside. Well, it's not really a spring, but actually it's a coil. And coil does sound similar to spring. And in anything, actually, a spring in German is actually called Spule. Spule. And Spule means coil. And Spule also means inductor. So this is like German, and this is English, and here is English. So going back to the point is that when we look at our second line of action, we have Fs2, which equals to IL2, which is equal to IR, because our damper is equivalent to a resistor, plus IL1. And here we have IR plus IL1 equals to I out, which is actually equal to 0. And when it's equal to 0, usually it means it's connected to ground. So now we have these mechanical systems. We convert it to electrical system. So using the current that we got, we take the one that is, I would say, the most complicated, and we take this one. So we know that we have IR, we have the current IR plus L1. So we know that an inductor, maybe like draw it like this. IL2 flows in this direction, and it splits into a resistor, we call, with the current IR, and it splits into an inductor L1, IL1. And we don't know for sure how it's going to connect right here, right now, but we know definitely this is the equivalent of this one. So when we look at this one itself, this one, we know that the I0 is equal to IL2. So since I0 is the input current, we could say that we draw a line like this, and here coming down you have U0, which is your initial voltage. So when we look at this one, then use different color. This one, we know that IR plus IL equals to I out, and it equals to 0. So therefore we draw a line like this. We say this is U out. And I made a small mistake, which I forgot to draw my inductor for L2. So this is how it should look like. L2. So yeah. So now we have transferred our mechanical system into our electrical system. The next thing we're going to do is we're going to try another example, and we're going to use something a bit more simpler. We're going to use something in series. So in series we have a mass. We don't have a mass. We have a damper connected to a mass, or we do have a mass, yeah. And we have a spring. So we determine our line of action here, center of the mass, and let's say we take a define the boundary, and we're given the question that this is F0. So again, let's label our spring. We call this S, and this is M and D. So we know our spring goes in this direction, spring goes in this direction. Our mass is gonna go in this direction because this is a fixed boundary, and here's not fixed, and it goes in this direction. So if it's A, so we know that Fm follows the direction of acceleration, and therefore the damper would then opposes the direction, and we say this Fd. So in our first line of action, we say that F0 equals to Fs. Fs plus Fm equals to Fd. Fd equals to F out, which is equal to 0. So remember, we're converting from effort variable to flow variable. Effort liquid to flow. So it means that I0 equals to IL, and here IL plus IC equals to IR, and here IR equals to I out, which is equal to 0. So now we can start sketching our electrical system. So within our electrical system, we would have something like, let's take this one for example. It's the most complicated one, so we're going to use this. So we say we know that an inductor current, let's call this IL, L. We know that this thing combines together with a capacitor. For this C, we call this IC. They combine together and they go to an R. So we say IR, and we don't know where this goes to. But we know here that the IR equals to I out. So we know this will be our free end. So we draw this thing. So we know this one goes like this, U out. Now from here, we know that the I0 equals to IL. So if we draw something like this, U0, we know the I0 equals to IL. So it's like this. I can make this a bit better. So we know it goes like this. However, we have a free end here. So the only way that this could fit in now is that instead of drawing it like that, we draw this down and we draw it like this. And this is our C. And it means that from here, it flows like this. I mean, I would say it flows like that, but the only sensible way is that it flow like this, I presume. But regardless, we know this is the correct electrical equivalent as given by our professor. Okay, so after further discussing with one of my colleague, we found out that it was not exactly equivalent to what the professor had given. So we can see that I put the capacitor here and the resistance here, but he put the resistance here and the capacitor here. And the truth is that if you put the capacitor here, it will be the same thing. But the question is, why is it like that? And I forgot a really important thing is that the professor mentioned in class is that our point of interest is Fm, not the Fd. So we should have written this as Fs minus Fd equals to Fm, because this is our point of interest. So then if we were to equivalent this one, we would get IL minus IR would then equal to IC. So if we were to make this equation, then we have our IL, and technically we say that if we and then we have our IR, and then we have our IC. So this one, right, if we were to flip it, it becomes a negative. So then when we know that our IL was equal to our I0, so we draw L, and we put something like this, and here you have your U0, U in, and we know from the top that is our IR equals to, our IR is no longer equal to IR, our Fm is our F out now. So therefore our I out is equivalent to IC. So IC would equivalent to like this. And we would put a ground here. And now it's UC, or we can U out. And now it's the same with the professor. Now we're going to work with another example. It's very similar to the one we did before, but this time we have a mass. And we have a mass, it goes like this, with a damper and a spring. And we say this is a free end. So we have a spring, a damper, and a mass. So we are also given in the question that this is our F0. And I'll draw my second line of action here. So we know the spring opposes the motion, and so does the damper, and your mass goes in that direction because acceleration is there and we don't have a boundary. So over here we say F0 equals to Fs plus Fd, Fs plus Fd equals to Fm, S0 equals to I0 equals to IL plus IR, IL plus IR equals to IC. So if we draw from here, we know we have a capacitor combined with a resistor, like that. Resistor, and then it goes out to this is IL, so this is inductor, and then resistor, and then here it goes to a capacitor. And we know that our IL plus IR equals to I0. So we draw like this. This is C, U0, U out, which is the same as UC. And we have ground. So yeah, this is how it would look like. And we can draw, make it a bit more better. IC, I0. Yeah, so this is how it would look like. So we're going to work on with another example. We're going to go from electrical systems to mechanical. So we are given the electrical circuit of an inductor. We call this L2 connected to L1 and it's connected to R, and draw a line like that. So we know that IL2. So given this alone, we can try to make the mechanical equivalent. So the mechanical equivalent would be, we know at this point we call it a node. At N, we say IL2 is equal to IR plus IL1. And let's call this node 1. And at node 2, node 3. So at node 2, we know that I0, because this would be I0, is equivalent to, maybe not I0, maybe we call it I in. So I in is equal to IL2. And we know that at node 3, we say IL1 is equal to I out, which is equal to 0. So if we convert this to our effort variable, we will get US2 equals to UD plus US1. And I in would be U in, not U in, it's not U, I mean it's force, not voltage. F in equals to Fs2. And here would be Fs1 equals to F out, which equals to 0. So we know that our Fd is in this direction plus our Fs1, and then our F2 is in the opposite direction. So if we had drawn this, we know that this is our damper, and then this is a spring. We call this D S1, and now we call this spring S2. given that our F in was F2, so we could say that our F in must have been in this direction. And Fs, no, actually, right? Because your F2 is in that direction, but here is your second F2, your complementary F2, Fs2. That would mean that your F in would also have to be in this direction. I'll put it here. And then your Fs1 is equal to your F out. So since equal to 0 should be like this. But it didn't specify on how we should write this. But in the professor, he wrote it as he wrote it like this, such that here F in Fc2 Fs2, and he wrote it that on here he wrote it that Fs2 Fs1 and Fd, and that is what the professor did. But that's kind of the end of my limit. I don't really know completely the reason why. I would argue that maybe if you bring F2 here, you become minus F S2. But then we saw in the previous equation, we could have done that as well. Why? So maybe it could have been possible that here was F S2, that here would have been F S2, and given that they were opposite the direction here, then yes, it would make sense to have F in this direction. Yeah,